Hi, welcome to the last session. We have two amazing papers. The first will be given by Guido Martínez, who works for MSR, research engineer. So Guido, take it away.
All right, thank you. Yeah, this works, perfect. So I'm going to tell you a bit about Kuiper, which is a language we're developing for doing safe, first of all, GPU programming, and also verifiable in the sense that you can prove that it's doing what it has to do, and also not relinquishing efficiency. And this is joint work with a bunch of people. A special shout out to Jonas, who was our intern last year. So the first question, of course, is why? Why do we want a language that's verified GPU programming? And the first and main reason is that GPUs are really hard, which is probably not surprising to this crowd. There's two different memories. You need to deal with this weird parallelism with the blocks and threads. You have barriers and asynchrony and memory hierarchies, and errors are kind of may go unnoticed at sometimes, and debugging is also hard. So it's like not a great place to be as a programmer. And performance is also like paramount. It's like pretty much. If you're using GPUs, you probably really do care much about performance, and we don't want to renounce full performance or have any kind of dynamic checks or sacrifice not be able to do what we want to do just because we have to avoid bugs and be safe. And we want very precise choice of like the memory layout and when we copy stuff and etc. So there's kind of this trade-off between safety and a correct program, and also being like 100% performance when you're developing at scale. So verification is kind of a way to get rid of that trade-off and do not trade performance for safety. You can do anything you want to do, use any fancy instruction or a pattern or whatever that you want to, as long as you just prove it that it's safe. So Kuiper is a language that starts with this mindset. It allows you to do many things. So it supports all of the usual suspects of GPU features. So there's heterogeneous memory, there's sharing between different threads, parallelism, asynchrony, and it's always memory safe and data erase free by construction. Optionally, you can even verify that your programs are doing what you want them to do. So if you write a fancy gem that's splitting the thing into 3 levels of tiles and sharing between different blocks and whatever, you can anyway at the end prove that it's actually just computing a gem at the mathematical level, and you don't need to trust the implementation. You just need to look at the specification. And there's 2 restrictions. You can write the fancy algorithm that you want, as long as you just prove it that it's safe. So far, Kuiper is relatively new. It's maybe like a year-ish old. We have like several flavors of gems, like fancy matrix multiplications, with no performance hit compared to a handwritten implementation. We also have programs using atomics. We have a parallel reduction implemented. We can do asynchronicity, like launching kernels asynchronously, use floating points, and do some forms of genetic programming. So like a very free style of polymorphism. Kuiper is built on top of F-star and Pulse. F-star you might know as this proof-oriented verification language. Pulse you might not know about, but you're kind of in luck because in Friday we have a paper about it on PLDI, so if you're curious, you can show up and listen to it. I'm going to show you a bit of Pulse today, which is kind of like the basics to get us going. Pulse is a language that's based on concurrent separation logic. That might sound a bit scary. I'm just going to give you like a primer in 1 minute of what this is about. So it's an extension to Hoare logic, so pre and post conditions, that makes reasoning about pointers and data more compositional. So the pre and post conditions in separation logic represent resources which can be spent. They're not just about truth. And threads own resources. So these are like the prototypes are simple functions like allocate a reference and free it. Allocate, in this case, I give it an initial value and it gives me back a reference. And as a post condition, it says R points to B. And this is, in a way, telling me that R does point to B in the thread, in the heap, but also that I own this fact. I am the single owner of this fact that R points to B. And then I can free it. So this other function free here has as a precondition that R points to B. And then when I call it, I give this precondition, I give this resource, and what I get back in the post condition is empty. I lose it. Once I free a reference, it's no longer there and I cannot use it. And then some resources like this one can be fractioned and shared. Fractioning means, for instance, if I have a reference that points to a value V, I can fraction this resource into 2 resources saying that R points to V, but I only know half of this and I only know another half of this. And then I can give this other half to another thread. And to read a reference, I only need a fraction of a permission. I don't need to be the single owner to read. So this is the way that concurrent read-only accesses are permitted in separation logic. So this frac notation is what represents a fractional resource. And then, for instance, this last thing is copying y into x. I only need some read permission over y. And then my precondition is that x points to some value x0. And my postcondition is that now it points to something different because I'm changing it. And I am the single owner. If it doesn't say, hey, frac, I'm the single owner of this resource. Yeah, so for instance, once you have this language set up, this is like a very tiny pulse example. If I allocate a reference 1, r, initialize to 1, I get the fact that r points to 1. I could free it, and then I lose this fact. And if I try to do anything with r after it, this fails. Like I don't own this resource anymore, and this is gone. So look into pulse if you're curious, or ask me about it at any point. So how does this help us in GPU programming? So I'm going to show you a very simple example of verifying a kernel thread. So this is an example of a kernel that takes 2 arrays in memory and point-wise multiplies them into a separate array, AR. So this is what I'm showing on the right here is actual Kuiper code. It has 3 parameters, A1, A2, AR, that are GPU arrays. There's a parameter about that is the thread ID of the thread that it's running. This is similar to thread ID, thread index.x in CUDA, but we make it an explicit parameter because it looks nicer. And the implementation inside the braces here, the body, is really just what you would expect. I read array A1 at TID, I read array A2 at TID, multiply the values, and save them into AR. Now, the implementation is direct. What about the specifications? So we need to add some stuff. So first of all, we need to say this function, when it's called, owns some fraction of the array A1 and some fraction of the array A2. So it is allowed to read them. If I did not own this, I cannot read them at all because they could be owned by some other thread who might free them, so they would be unsafe. When I say preserves, it means something that is required and also given back at the end. So we take some permission on A1 and A2, we give it back at the end. And the requires, another part of the precondition is that we know and we own that the TID cell of the result array points to something. And in the postcondition, we say we change this V0 value, and now it points to something else, which allows us to write over this thing. And this one is full permission over the cell. So this is like the separation logic specification that you would expect for this function. In Kuiper, we need to add a few more things to make this actually into a GPU kernel, basically. We need to mark this function as a GPU kernel. This thing is kind of a token resource that we use just to mark that this thing will run on the GPU, and it can be spawned into a thread group, and it can use GPU-only operations like barriers to synchronize and etc. Another thing is that we need to explicitly encode the grid constraints. So if I'm saying that this function will multiply 2 arrays of size len, this needs to run in a block of size len. I cannot just run whatever number of threads I want. If I want this postcondition at the end that they actually multiply to arrays, we need the block to be the proper size. So this is encoded in the specification as well here. And then when we're verifying and trying to get decent, reasonable properties out of this, we need to add some proof steps once in a while. So in this case, if we want to verify that at the end we get the point-wise multiplication of these 2 sequences, there's some convincing that we need to call to do to get Pulse to accept this. So it's those final 2 lines. But if we only care about safety and we just want a program that we know will not crash and will not have data races, this can be removed just by weakening the specification and saying AR_TID points to some other value, some new value. So how do we execute these things? So I'm showing you this fancy language that looks kind of different from CUDA or something, and it has the specifications. The way we execute these functions is by extracting them into CUDA-C. So after we check these functions in Pulse, or in Kuiper, we extract them and we get code that looks exactly like this, actually. So it's pretty much what you would expect. The code is somewhat readable. All of the specifications and proofs are gone. You just get plain CUDA-C code out of it. Without any kinds of dynamic checks. We don't do any kind of transformation in that sense. And this can be used directly by CUDA clients. You don't need to buy into to write your entire program in Kuiper to be able to use it. Does it kind of make sense so far? Good. So I was just showing you how to verify one single thread in a way. This is the function that executes one single thread. When we want to spawn a kernel, we have some big resource, like I have 2 of my input matrices AB, and I want to write the product into a matrix C. So I need to split these resources and to be able to spawn a big kernel and allow them to compute. So the way this looks like in separation logic is roughly that at the beginning, as the main thread of my function, let's say, of my program, and this is just a CPU thread, I fully own A and B, and I fully own C. And the first step I will do is split these resources in some interesting way. So for instance, let's say I'm going to spawn, let's say 16 threads, but they don't fit on the slide, so I'm just going to show you 4. I'm going to spawn a bunch of threads, and I want every thread to be able to read from A and B and to write into a single cell of C. So the steps you need to do is take the matrices A and B and share them across all of the threads, so in 16 equal pieces, and everyone gets some fraction of permission. And the output matrix, it's a different kind of sharing. We explode it into cells and give to every thread full ownership of a single cell, so they can mutate it, but they can do nothing else with the rest, don't even read them. After we do this, you can spawn a big kernel that works. Every thread works on one of these output cells. They modify them somehow. Now they make them purple. They cannot really modify the inputs because they all share them. So sharing modifying them when someone else can read them is a data race. And then at the end, we'll also join all these resources and get back, full permission over AB and full permission over the now modified C. And I should say, all of the computation really happens in this middle step. Here, when I say all of this stuff, sharing resources and slicing the matrix and all this, these are all ghost steps that don't have any computational meaning. They're just to convince, they're just proof artifacts in a way. So with that in mind, the way we model kernel launches in Kuiper is, if we consider launching n threads, let's say we have a simple example of, let's launch one block of n threads, and that's it. And every thread I, the thread index I, has a precondition pre-I and a postcondition post-I. So if we want to launch all of these threads in parallel, what we have to do is provide at the beginning each of the preconditions of the threads separately. We need to be able to split split our resources into separate compartments where each thread has its own preconditions separately from the others. Then we can run all the threads in parallel, and we get back all the postconditions separately. Now this is generic enough, but it's in a shape that's not really useful. So the pre and post conditions of the full thing have a simpler way of, usually have a simpler way of expressing them. So we add some ghost steps to tweak it. So the kernel specification looks most like there is a big precondition and a big postcondition, and then there is a way to split the big precondition into the individual preconditions, run the threads in parallel, you get the separated postconditions, and then you put them all back together into post. So at the end, this looks more like, okay, you give me permission over the full matrix, and I'll give you back permission over the full matrix at the end. Even though in the middle, it's all shared in this slicing and sharing and this kind of interesting patterns. And here, this was an example of just one block of n threads. Usually, a grid is, at least has 2 levels, so you have to spawn blocks, and each block spawns a number of threads. So the same idea applies, just recursively. You do this 2 steps in a row. And it allows you to capture the specifications of more complicated grids. So once we have this kind of proof done, we can package it into what we call a kernel description, which means that, so there is a type in Pulse called k-description that says, this is a package of a kernel that goes from pre to post, and it does so by calling some kernel function, and it has some grid size, and here are the proofs that show that this is all correct. And once we defined an element of this type, we can forget about all the details of the kernel. This is all irrelevant, basically. And since they encode the grid size and all of that, we can just spawn a kernel description. And the function that spawns a kernel looks something like this. Give me a kernel description that goes from pre to post, and I require pre, and I ensure post. And that's it. And then everything else is happening under the covers. And there's no messing up, when you spawn a kernel, there's no messing up the number of blocks and threads and etc., which can happen in CUDA. This is all encoded in the record. Does this make sense so far? So another of Kuiper features is that going beyond like the safety and the way the separation logic is involved is that we make heavy use of polymorphism and specialization. So Kuiper inherits polymorphism and type classes from Pulse and F***, which we built up on top of. So in this example here, this is a type of a matrix multiplication. It's polymorphic over the element type of the matrix, so the type of every cell, as long as that type is scalar. This is a type class constraint in F***. The type being scalar just means that it has a plus and a product, and a 0 and a 1. And the implementation here is completely parametric over the type we're working on. And when you choose a type, you can specialize this and generate specialized CUDA code that works over the particular type without any runtime, like dynamic dispatch or anything like it. You can also use this, for instance, if you want to compute shortest distances in a graph, you can instantiate this with the min and plus semi-ring, as Amir was telling us this morning. And this allows you to just reuse your matrix multiplication and specialize it to compute shortest distances in a graph at no cost. Right. Going a bit further than this, actually, we can write programs that are not only polymorphic over the type they work on and the operations they work on, but also on the matrix layout. So I keep saying we have these matrices that are in memory some way. There's many representations you can use for matrices. The two most basic ones are like row major and column major. So ideally, I would like to write my algorithms just once and then just instantiate them for different layouts. And Kuiper supports this in a very comfortable way. So in the type you see here on the right, it's saying this function takes three matrices, GA, GB, GC, and they have some layout, LA, LB, and LC, and this is defined in some way in F star. And there is a type constraint saying that the layouts have to be concretizable and computable. And the layout, the only thing that the layout is defining is where does the cell ij of the matrix go in memory. And if it's row major, it's I times columns plus j, and if it's column major, it's the dual. And this layout doesn't even have to be regular. If it's a fixed size, like any crazy bijection works. If you're working over matrices of 4x4 and you decided that you want to store them by rows, but some row is backwards or whatever, this can all be modeled in Kuiper. And every function we wrote is genetic on top of this. And specialized implementation is also possible. So we're currently looking at trying to model tensor cores inside Kuiper, and we will definitely need to have specialized, they use a given particular representation, so those are not polymorphic in a way. So all of these algorithms, we write them in this very polymorphic and specializable way. And once you do this, you can specialize a given function. So for instance, here's this matmul GPU function here is a very polymorphic matrix multiplication, and there's a specialization function that says, okay, specialize it now to floats, and the two inputs are in column major, and the output is in row major. And out comes this code, which is kind of reasonable CUDA for this. And if you look closely, you will see that the array accesses to GA and GB happen in column major, and that the access to the output GC happens in row major. But I didn't have to think about any of this when I wrote this. We just verified this once, and we also verified what column major and row major mean only once, and then we get to specialize every combination of these functions. So we're getting this specialized verified kernels for free with the same guarantees, and there's no runtime hit. This CUDA code is exactly what you would expect. And any parameter is specializable. So I've been telling you about the type and the operations and the layout. Another important parameter here that you can specialize is the tile size. So you can define many versions of matrix multiplication that copy tiles into shared memory and do this a couple times. And the tile size is a very important parameter. So what you do in Kuiper usually is you define a function that does this where the tile size is just an argument, so a dynamic argument. And you verify this function. And then you can choose to specialize it to 2, 4, 8, 16, 32. And then you tune it to see which one works best. And it's easier to tune in a way. This allows you to tune more easily, since you know every version is correct. They are all correct by the fact that you verify the genetic one. So just a minor fact, we also support some basic forms of rotation fusion. So if let's say you need to compute the product of A and B, A times B transposed, well, what you can do is compute A times B, let's say they're in row major, you do the product into column major representation into some buffer, and then if you just flip your view, this is really the transpose in row major. So this can all be proven inside the tool, so you can avoid like spurious steps of transposing and etc. Today, by the way, with this specialization trick, we're generating around 15,000 lines of CUDA from around 15,000 lines of F star, or pulse or Kuiper. This ratio is usually much lower, but the exponential verification here really kind of gives us an edge. Some more fancy features that we support as well are barriers. So in a block, usually you need to synchronize between the threads, and so the way a barrier works in CUDA is all of the threads have to reach a barrier before they can all go. And this allows you to make sure that some things have been copied or whatever you're doing. The way we model this in Kuiper and in separation logic is that barriers have a precondition P that the threads have to provide. So from 0 to n-1, let's say there are n threads. Each thread has to give P of 0, P of 1, P of 2. So thread I has to give P of I into the barrier. And then when they all get there, we model that there is some ghost shuffling of resources that happens. And every thread comes out of the barrier owning Q of I. So thread 0 gave P of 0 and gets Q of 0, and the same for every other resource. And the only proof a user needs to do to show that a barrier is correct is that this is actually a shuffle, that if you take all of the P's, you can turn them into all of the Q's. This is useful, for instance, if you're using a local cache, like if you're copying global memory into shared memory, which all of the threads in a block share. You use them to say, at the beginning of the iteration, every thread in my block owns a single cell of this array. So the barrier, the precondition of the barrier is that I own a given cell of the array. And the postcondition of the barrier is that I own the full matrix with just some fraction. So then what happens when you call sync threads is that after this, every thread owns a fraction of the matrix. And then you can also go back with the same barrier to the previous state and keep copying memory back and forth and sharing them between all the blocks and the threads, all the threads in the block. Sorry. Another a bit more fancy feature that Kuiper supports is asynchronous kernel launches. So usually, in CUDA, launching a kernel does not immediately wait for it. It's just launched and scheduled into the GPU to be executed, and you can spawn many of them at once. We also model this in Kuiper and allow you to reason about this stuff. So the way this works is we use a reasoning principle for this kind of stuff called pledges. You can see our PLDI paper on Friday for a deeper explanation of it. But a pledge is kind of like a coupon that tells you what will happen in the future and how you can get it. So the key reasoning principle of a pledge, it looks kind of like an implication. A pledge says that if I own P, and I also have a pledge that whenever P holds, you get Q. So pledge PQ, you should read it as kind of a coupon that tells you that you can cash it in. So then when P holds, you get to keep P and also obtain the postcondition Q. And the way we model this asynchronous launches is that if I want to launch a kernel that has some precondition pre, I need to give the precondition so the thread can execute. And then what I get at the end is the most important bit is this pledge that tells me when the current epoch is done, which I'll tell you about, but that is in a minute, then you'll get the post, but you don't get it immediately. And the way you get that the epoch is done is by calling sync device. And sync device basically advances this epoch counter and tells you like, okay, the current epoch is now done. You've waited for it. So then you get to call redeem pledge repeatedly over every block, every kernel you spawn to get all the post conditions. Yeah, so that's about what I wanted to tell you. Kuiper is this framework for writing generic verified kernels at zero cost. So far, we don't want to compromise on performance. So everything we're doing, we're generating very first-order CUDA code and checking that it's actually at the performance we expect. We cover a decent chunk of CUDA, so different grids, shared memory, barriers, atomics, floating points with many precisions, asynchrony. We can also prove some stuff about floating point computations, but I didn't have time to go into that, but ask me if you're curious. We verified several building blocks already, many flavors of matrix multiplications. We have a parallel reduction using barriers, another parallel reduction using atomics across blocks, and asynchronous invocations, and etc. By the way, this table right here is for many different implementations of matrix multiplication. The ones that are not in bold font are just handwritten that we, just normal CUDA code, getting closer to kubeless-like performance. The best one we've done in Kuiper is this 1D block tiling, and we actually beat the performance of the original CUDA code that we were mimicking. For the others, we're pretty much exactly the same because the CUDA code is really exactly what you would expect. And we plan to keep going forward. The things we now need to make a bigger dent in this, to get closer to 100% is like warp level operations and tensor cores and etc. Yeah, so I'm going to do a shameless self-plug. So after this session, I'm going to be at the Microsoft booth. I'm going to give a demo of this stuff. So if anyone is interested, you should feel free to come and chat. And yeah, I'm happy to take any questions. So thank you.
Thank you. Questions?
Cool. Thanks for the talk. So one question I was going to have is, have you guys looked at, so like Cutlass and Qt have built a bunch of abstractions that actually have good semantics, I think, for doing this kind of thing, where, for example, like Cutlass exposes an atom, which is like a MMA atom, and everything is defined in terms of these layouts that are algebraic. And so you could actually define them, I think, where the precondition, postcondition would sort of have like an if statement and it effectively like what level of the hierarchy you're doing, but they're modeling copying from shared memory to global and back to registers. But I think it actually would be a good abstraction to think about because they've sort of done some of the modeling, and then the layouts that they have are more general, and that you can use them to cover not only the modes of that you have here with like column, row, major, et cetera, but like complicated tilings and shuffles. And I don't know if you guys have looked at that, but I think there's something, my verification head and my kernel writing head or see like a connection here that I think would be useful.
Right, we haven't, but that's a great tip. Thank you.
Yeah, the layouts in general are complicated. I'm happy to talk about it afterwards, but I think it generalizes everything to like a layout is a pair of a shape and a stride that generalizes like bijective, or there's a bunch of conditions on them, but they have like co-operations, et cetera.
Right. So for now, our layouts are kind of basic in the way that they're just a bijection from ij into a position in an array. So we don't particularly model strides so far. And this means we don't allow you right now to take like a submatrix because then you need a stride. But we should definitely extend it to do this kind of thing. So yeah.
Right. The cool part is the copy operation then becomes generic. So I think you could write a generic pre-post condition, and then you could write an implementation ideally that doesn't have to mention very much because it's sort of discharged by the condition of the atom in quotes. So anyways, it's something we talk about. But
yeah, nice. Thanks.
Time for one more question. Anyone in the back, please?
Thanks for the talk. Could you speak a bit more about the GPU resource? Does it have a definition, and how do you use it in the verification? Because a lot of what you present can also be applied to parallel CPU programs. Right?
Yes, so the GPU resource, you're right, it doesn't have a definition, it's more axiomatic. So we use it to control what you can spawn. So when you're writing CUDA C, you cannot just put like triple brackets on any function. It has to be a global, it must have been marked with the global attribute to say that this is a kernel and you can spawn it. So the GPU resource is kind of what we use here to model this restriction, but it really is an opaque resource which is passed back and forth. So what we should probably really do is have a mode system in Pulse that allows you to say this function is GPU, and it's a different kind of function from others. But this resource thing kind of gets us most of the way there, but it doesn't have a definition. Yes, good catch.
Thanks. I have one question. I was not sure whether that while loop, if changed slightly, will give a problem. I haven't analyzed it fully. You had a while loop.
This one?
Yeah. Suppose we make the k thread ID x or something like that. Then that sort of means that each thread will do a different number of iterations because the shared comes in from outside. So would that will be a data dependent loop? So I wasn't sure how.
So k is initialized as 0.
I know,
right?
but
okay.
I'm looking at thinking of a different program where that k might be TIDX or something, thread ID. So you're comparing my thread ID with something that comes from above. So each thread will iterate a different number of times. Am I right? In that case, the amount of read-write accesses each thread performs is a data dependent. Yeah, so I should work out, I don't know, yeah. So there could be, in general, data dependency is handled properly by permission-based separation logic, but I haven't thought through it. Do you have you run into any cases where that might cause an issue or not?
So not yet.
Not yet, okay.
But I think most of these things, so for instance, we're not
because
proving...
for every read, you get, you don't take any permissions for every, you take a fractional permission and things like that.
Right, but it's not spent. So we don't do any kind of reasoning of like, every thread runs in the same constant time, or they use the same memory access. We don't do any of this right now.
Should be good.
But we could possibly do it, I think.
Yeah. Let's thank the speaker once again for a great presentation.
Thank you.